Good morning, everyone. My name is Anuda Pansilu, and today I am presenting my research on developing an integrated machine learning framework for soil health prediction using microbial and environment parameters. This work was conducted as a part of my MSc in Advanced Computer Science at Cardiff Metropolitan University under supervision of Dr. Tahir Sabin. Soil microbes are hidden workforce that drives nutrient cycling, carbon, and nitrogen processes in ecosystem. However, with modern agricultural intensification, we are seeing a loss in microbial diversity and decline in soil health. While a lot of research has focused on surface soil, subsurface layers, especially 10 to 20 centimeters deep, remain poorly understood but are key for long-term sustainability. My project aims to address this gap by leveraging machine learning to better predict and manage soil health, supporting more sustainable agriculture. The main goal is to predict soil health by modeling the complex interaction between microbial communities and environmental features using machine learning. More especially, I want to compare microbial communities in surface versus subsurface soils, understand how land use soil properties affect microbial enzyme activities, and finally, develop and deploy a practical machine learning prediction tool accessible through a web interface. From literature, it is clear that intensive agricultural practices like monoculture and heavy fertilizer use tend to reduce microbial diversity, negatively impact nutrient cycle. In contrast, organic farming and crop rotation can boost microbial richness and resilience. Subsurface soils, while less diverse, contain specialized microbes that play a vital role in long-term carbon storage and nutrient turnover. Given the complexity of soil and microbial data, machine learning is emerging as powerful tool for revealing pattern and making accurate predictions. I used Kaggle soil microbe dataset, which include tropical soil samples. Key input features include soil pH, organic carbon, nitrogen, land use types such as monoculture, organic or traditional, microbial abundance, data for bacteria and fungi, and the depth at which the sample was taken. The target output for prediction are activities of glucosides and urease, CO2 emission rates, and nitrate NH4 nitrate content. This gives us a comprehensive view of both the chemical and biological dimensions of soil health. My machine learning approach centers around random forest regression, which is robust for multi-output tasks. Data preprocessing include handling missing value, encoding categorical value, and engineering new features like carbon-nitrogen ratio. The dataset was split 80% for training and 20% for testing, maintaining a balance between different land use and depth categories. I also optimized the model through grid search and cross-validation to ensure reliable performance. Here's a high-level view of the system. Users enter their soil and land use through a simple web form. The data grows through pre-processing and feature engineering steps. The trained random forest model then predict microbial activities and nutrient cycling outputs. Results are displayed using clear labels like best or not good to guide user understanding. All interactions are stored in a MongoDB database for tracking and future analysis. The entire work is accessible through a user-friendly Flash-based web application. The model showed strong predictive ability. R-squared values between 0.73 and 0.81 for the main target, indicating that the model could be explain most of the variance in microbial enzymes and nutrient cycle. Key predictors identify soil depth, land use type, soil pH, organic carbon, carbon nitrogen ratio, and microbial abundance. This highlights the importance of both environmental and management variables in shaping soil health. To make this tool accessible, I developed a web application using Flask. User simply enters soil data and the system instantly provides predictions and, and assessments for soil health. The tools also generates actionable recommendations, for example, suggesting organic amendments or crop rotation when needed. All data is stored so user can track changes over time. The bridges the gap between advanced data analysis and real-world decision making for farmers and researchers. Here, this is my web application demo. The prediction are shown as best, better, good, not bad. Here, this is my web form that take the data from user to predict the output. These are the four outputs for the predictions in my web application demo. These are the final result that the user gets from the web application demo. The key contribution of my project is the integration of death-resolved microbial data and machine learning into a practical, user-friendly tool. The framework offers actionable, data-driven recommendations for sustainable land management and is accessible not just to researchers but also for farmers and policymakers, promoting more informed and sustainable agricultural practices. As with any research, there are limitations. The dataset covers specific regions and time frames, and there's less information available for deep subsurface soils. For future work, I plan to extend data collection to more regions and different seasons, integrate multi-omic data for even richer insights, and focus on explainable AI models. Eventually, I hope to enable real-time sensors based on soil health monitors using this approach. In conclusion, machine learning provides a powerful way to predict soil microbial activity and nutrient status, even across different depth and land use practices. The work demonstrates that integrating machine learning with soil science can directly support sustainable agriculture, closing the gap between researchers and practical land management.